We've been dealing with Lewis structures and looking at how valence electrons interact, especially in covalent compounds. Well, now we're going to talk about VSEPR, and VSEPR is specific to molecules. In other words, molecules have unique shapes, and these shapes can actually be predicted. And this is based on the number of bonding and non-bonding electrons, which is what we look at when we look at Lewis structures. A couple of reminders about what you know. We already know that electrons are going to interact. We know they have like charges. We know that these like charges repel. We know that different orbitals have different distances from each other, and all of this together means that we know that electron pairs are going to basically be as far away as possible from each other. Now, to start with, we always do a Lewis structure. Lewis structures are really important because they give us a couple of things. They tell us the number of bonding and the number of non-bonding, or more specifically in this case what we care about, let me get red here, is what we call non-bonded or unshared pairs. And these are really important in terms of the shape that we observe, because if an electron is going to avoid other electrons and they're in pairs and they're having to occupy a particular space, they're literally going to try to shift as far away from each other. And that means that we can actually predict the shape of our molecules based on the three-dimensional location of these electron pairs, because ultimately what's going on is all of these atoms are trying to minimize the repulsive force. So all of the electrons are trying to get as far away as possible from each other and still be shared between atoms. Okay? So it's ultimately this idea of minimizing our repulsive force. This is obviously where our theory gets its name. The idea of valence shell electron pair repulsion is the idea that molecular geometries can be predicted if we know that electrons want to be as far away as possible from each other, and they're limited within a three-dimensional space. Now, for example, as we've already stated, you always start with a Lewis dot diagram. Now, once we do that, notice what we now use. We use a couple of new terms or representatives. We have an A for the central atom, okay? I'm going to use green. We then have an X for every atom bonded to the central atom. And then we use an E for any lone pairs. So if we have a lone pair on the central atom. Now this is only on the central atom. Okay? So the first example is going to be AlCl3, aluminum chloride. And we know the number of electrons it has. We know that aluminum needs to be put in the center, that we put Cl's around it, and ultimately we end up with this idea. So if we use our VSEPR notation, all right, we know that Al is represented by A, Cl is going to be represented by X. We get a particular formula, AX3. Now this is listed in page 200 of the Holt book. You will also have a handout associated with the different molecular geometries. What's cool is that since the geometry is predicted, every geometry has a unique name. So the name for this particular geometry, where we have what's known as AX3, is known as trigonal-planar. Planar tells you that it's flat, trigonal tells you 3. So we see literally a very flat structure. Now, when we compare that to something like PCl3, which produces this Lewis dot diagram, notice that we have these unshared pairs of electrons. That changes our VSEPR formula. It also changes our shape. And we produce what's known as trigonal-pyramidal. In other words, the presence of these lone pairs of electrons shifts the shape in such a way that it almost looks like a mini pyramid. Now, another example would be water. Water now has what's known as AX2E2. In other words, I have two sets of electrons on the central atom. These are going to affect the shape, producing what's known as an angular geometry. Now, bent and angular, you see these two terms used simultaneously, but it kind of depends on the general structure from the Lewis structure. Now, ultimately, when we talk about VSEPR, let's go back. The point of VSEPR really is to understand the reactivity in our compounds and recognizing the role of electron pairs in the shape. In other words, each of these shapes, and so you can see here's our trigonal-planar, here's our pyramidal. Each of these shapes is predicted and predictable by the Lewis structure that we build. And because ultimately all of our bonding and non-bonding electrons repel and they want to get as far away from each other to minimize these repulsive forces, we see the effects of these paired and unpaired electrons. Now, one of the points, the reason that we see a trigonal pyramidal versus a trigonal planar and the difference in shape has to do with this right here. Unshared electrons have a greater repulsive force than bonded pairs, and this is because the unshared pair get to literally occupy a little more space because they're not bonded. They're not limited in scope in terms of the space they have to occupy. So they literally have a greater repulsive force. So when we look at a trigonal planar versus a trigonal pyramidal, the extra electrons that, for example, would be right here coming towards you would actually cause these bonds to shift away from it, which is why when we looked at that one shape, the trigonal pyramidal is slightly pyramidal. They literally, you can see how these literally shift down away from the unbonded pair up here. So, final points. The structure of a molecule in a polyatomic ion or any molecule can be represented by a Lewis dot diagram. We show the pattern of shared and unshared pairs of electrons. VSEPR is a method of using the Lewis dot diagram to predict molecular shapes. And if we know the Lewis dot diagram and we know the VSEPR formula, we know the shape that those molecules are going to form because we can recognize in a three-dimensional space where the electrons need to be to minimize the repulsive force. And therefore, ultimately, and the whole point of this is that we can predict any molecule's shape based on the electron repulsions.